All right, our next focus on the free response here deals with a table, and we want to look at how tables can be used on the free response section of the AP Calculus exam. Specifically, we want to look at things that we want to pick up on right away in the question. So, as a pot of coffee cools down, the temperature of the coffee is modeled by a differentiable function. And again, students may hesitate a little bit when they see those kinds of things, but maybe they're not quite familiar with the idea that something, you telling me that this function is differentiable is kind of a big deal, because what you've actually told me, right, by telling me that, is that the function is continuous, right? So that might set up, and again, we're looking down the road, that might set up the use of mean value theorem, right? Intermediate value theorem. I mean, there could be a lot of things that come from that. Students don't typically think ahead like this, and I think if we could get them to think like that after just reading one sentence, then I think that's important. They're ready. They're priming themselves to do well. You've given me a closed interval. That could set me up for extreme value theorem, right? So time is measured in minutes, temperatures in degrees Celsius, and then they give us these temperatures in the table below. Now, let's pause for a second. Why should I care about the numbers in this table, right? Obviously, we're going to use them in some way, but look carefully at the minutes, right? The thing I always like to point out to my students is, look at something like this, unequal spacing, unequal intervals, if you will. Why is this important? Because later on, if you ask me to do a Riemann sum or a trapezoidal sum, I need to understand that it is not as simple as just putting the width outside, right, while I go and continue to do all my length calculations and things of that nature. So I want students to be aware that I can't just do 12 minus 0, divide it by 4 or 5 or however many intervals they'd like, and just take that quote-unquote average width, when in reality, the width varies as we go, 0 to 3, 3 to 5, so on and so forth. So all very important things that we can pick up just in this first minute of analyzing a problem. Now let's dive into the parts themselves, right? So part A says, I'd like you to evaluate from 0 to 12, C prime. Well, when you evaluate C prime and when you integrate C prime, you get yourself to C, right? So this would be C of t evaluated from 0 to 12. And so what they're asking me to do here is simply just do C of 12 minus C of 0, which is exactly why we have the numbers in the table, and that will give us negative 25 degrees Celsius. So we've indicated units of measure. We've done what they want. Explain the meaning of your answer in context of the problem. That means I need to do a couple things here. I need to make reference to the coffee itself. What is it doing? I need to make reference to the time involved, the 0 and the 12. So we could say something as simple as the coffee, right, has cooled 25 degrees Celsius during the time period t equals 0, whoops, didn't write that so legibly there, to t equals 12. So nice and simple like that. I mean, we could do something as the coffee, total temperature change in the coffee is 25 degrees, has gone down 25 degrees, anything of that nature, but we want to make sure we're referencing back to the coffee. Make sure we're not using words like it or the function or something like that. That's not really contextual in this case. Let's look at part B. Right now what they've done is careful here, students have to notice that this is not C prime anymore, right? And they've gone to just the integral from 0 to 12 of C of t with this 1/12 over. Again, I want my students to realize right away that they're asking me to do the average, right? An average value. This is very important for students to pick up. And as we talked about before, here's this trapezoidal sum you're asking me to do with 5 subintervals, and they're not equal widths. So we're going to make sure that we have the 1/12 outside, and then I give my students the choice. We always talk about, we've discovered earlier in the year, that another way to get a trapezoidal sum is to average the left and the right Riemann sum. So they may do that. Some students may choose to do the actual trapezoidal approximation. We just want to make sure, I always want to make sure that we are highlighting the idea that you've got to make sure that you use 1/12 in there as well. So after the calculations here, if you've gone ahead and figured them out, you should get an average temperature of this pot of coffee of 49.917 degrees Celsius. And during these times where we have decimal answers, let's also remember, and we saw this in the last free response, I just don't think it ever gets too old to say, to students, make sure we are rounding appropriately, minimum of 3 decimals as we go, right? Let's make sure they don't round in the middle of a problem and they wait until the end of a calculation. Okay, part C, and there's 4 parts to this problem. So part C, use the data to approximate, right, at the rate at which the temperature is changing at T equals 4. Now, if you remember from the table, let's go back here for a second, right? There is no 4, but there's a 0 and a 3 and a 3 and a 5, right? So 4 obviously falls right between 3 and 5. So I think it's best here if students just stay locally linear. That's what we're asking here, right? And we just do C of 5 minus C of 3 over 5 minus 3. Just f of b minus f of a over b minus a there, right? And we get negative 7/2 degrees Celsius per minute. Remember, it's a rate now, so we want to highlight the units there as well. If you keep seeing indicate units of measure, tell students that probably means that in scoring they will be awarded a point for units. Okay, and finally, part D. For 12 to 15, so now they're going beyond the table here, which throws students for a loop a lot of times. The rate of cooling is modeled by this function. It's a trigonometric function, so it's differentiable. We don't have to worry about that for cosine here. Based on the model, what is the temperature of the coffee when T equals 15? So this is where C of 12 becomes so important. So C of 12 was 40 degrees Celsius, right? So what we have to do here is get the total change in temperature in the next 3 minutes and add that to that initial temperature. So we want students to show that setup. I'm going to start with 40, and I want to integrate from 12 to 15. Always remind them they don't necessarily have to write the function out if they don't like, if it's notated by something, in this case C prime. And we should get a pretty clean answer here of 35.130 degrees Celsius, which goes in keeping with the idea that the temperature should be a little smaller here than 40. So I hope this free response focus has been helpful on how we can work through some tables and interpret some meanings of various things. Again, as I always say, if you see opportunities to extend the problem for your students, do so. I mentioned earlier that you could play with a mean value theorem or intermediate value theorem at some point and ask them perhaps, is there a time at which the temperature of the coffee is such and such? That would be a nice thing to think about. So anytime you can add on to that, time is limited sometimes, but I think it really helps for the student to see outside of the problem that they're dealing with.